One element changes everything completely. Carbon wears countless different identities. Diamond, graphite, life share, carbon, same atoms, different extraordinary structures. 6 protons create endless possibilities. Arrangement changes every physical property. Structure determines material's true identity. Geometry changes everything about carbon. Diamond seems incredibly mysterious initially. Graphite appears completely ordinary instead. Both contain identical carbon atoms. Different bonding creates opposite behaviors. Carbon surprises scientists every generation. Hidden rules explain remarkable transformations. Hardness depends upon atomic arrangement. Electrons control fascinating material properties. Carbon builds Earth's strongest materials. Carbon also creates living organisms. Everything begins with structure alone. Carbon's secret changes perspectives forever. Most people wrongly assume different materials always require completely different chemical elements altogether. Diamond and graphite contain nothing except pure carbon atoms with identical atomic composition. No hidden ingredients or impurities create their dramatically different physical characteristics whatsoever. Their entire difference originates from how carbon atoms connect inside crystal structures together. That geometric arrangement transforms identical atoms into astonishingly different materials with opposite properties. Understanding carbon means understanding atomic architecture instead of merely memorizing chemical compositions alone. Diamond represents carbon arranged into an incredibly rigid three-dimensional atomic framework throughout. Every carbon atom forms for strong covalent bonds with neighboring carbon atoms permanently. Those tetrahedral bonds extend endlessly, creating an extraordinarily stable repeating crystal lattice everywhere. Weak directions simply do not exist within Diamond's remarkably interconnected atomic framework anywhere. Breaking Diamond requires disrupting countless interconnected bonds across every possible structural direction simultaneously. Diamond's exceptional hardness results primarily from its rigid three-dimensional bonding network structure itself. Surprisingly, individual graphite bonds exceed diamond bonds in intrinsic chemical strength under measurements. Diamond remains harder because its structure prevents layers bending, sliding, or separating easily. Its tightly bound electrons cannot absorb ordinary visible light passing through the crystal. Visible light therefore travels freely, making diamonds appear brilliantly transparent and sparkling naturally. Diamond's remarkable beauty originates from electron behavior instead of mysterious magical properties entirely. Now consider graphite, containing identical carbon atoms arranged completely differently from diamond instead. Every graphite carbon atom bonds with only 3 neighboring carbon atoms inside sheets. Those atoms create flat hexagonal layers resembling endless interconnected chicken wire patterns, extending continuously. Individual graphite sheets possess exceptionally strong chemical bonds holding neighboring atoms firmly together. However, neighboring sheets remain connected only through extremely weak attractive intermolecular forces present. Writing with pencils simply peels graphite layers onto paper instead of breaking bonds. Graphite's remaining electron becomes freely mobile across each hexagonal atomic sheet continuously instead. Those mobile electrons allow graphite conducting electricity while remaining soft and easily smudged. Graphite appears black because mobile electrons absorb nearly every visible light wavelength completely. Diamond remains transparent because tightly bound electrons cannot absorb visible spectrum energy efficiently. Carbon black forms when combustion lacks sufficient oxygen for orderly crystal growth processes. Rapid cooling traps, carbon atoms inside, chaotic disordered arrangements instead of organized lattice. Soot, charcoal, and carbon black all belong to this highly disordered carbon family. Their irregular electron networks absorb almost every wavelength, producing deep black appearances consistently. Carbon black quietly surrounds everyday life despite remaining unnoticed by most people worldwide. Printing inks, paints, toners, and automotive finishes all depend upon carbon black pigments. Rubber tires gain their familiar black color from reinforcing carbon black additives throughout. Manufacturers classify carbon materials into hard and soft varieties based on graphitization behavior. Hard carbon stubbornly resists transforming into graphite despite extremely high processing temperatures applied. Soft carbon readily reorganizes into graphite when exposed to sufficiently intense heat conditions. Modern battery technology depends heavily upon these contrasting carbon structures for efficient performance. Hard carbon stores impressive lithium quantities because spacious disordered structures welcome incoming ions. Soft carbon often becomes artificial graphite, serving different essential battery component applications worldwide. Even simple soot represents countless partially formed structures rather than one identical substance. Carbon's versatility continues, astonishing scientists through increasingly remarkable discoveries every passing decade today. Imagine removing only one atomic layer from ordinary graphite without damaging its structure. That impossibly thin sheet becomes graphene, among humanity's strongest materials ever measured scientifically. Graphene combines extraordinary strength with astonishing thinness, unlike any conventional engineering material known. Scientists discovered carbon forming hollow spherical molecules resembling stitched soccer balls beautifully. These molecules became famous buckyballs, revolutionizing chemistry through unexpected atomic architecture discoveries worldwide. Their groundbreaking discovery earned prestigious Nobel Prize recognition for pioneering researchers involved later. Rolling graphene sheets creates nanotubes possessing extraordinary strength and remarkable engineering possibilities ahead. Researchers investigate nanotubes for advanced armor, aerospace structures, electronics, and future revolutionary technologies. Scientists continue discovering entirely new carbon structures under extreme laboratory experimental conditions regularly. Extreme pressure and heat created carbon stronger than ceramics while remaining surprisingly elastic. One element repeatedly reinvents itself through endlessly different atomic arrangements and remarkable behaviors. Carbon's greatest achievement extends beyond materials because it also makes life possible itself. Every living organism ultimately depends upon carbon's extraordinary ability forming endless chemical structures. Carbon forms chains, rings, branches, networks, and unimaginably complex molecular architectures effortlessly today. No other element matches carbon's extraordinary versatility across chemistry and biological systems alike. DNA, proteins, fats, and sugars all rely upon carbon's remarkable bonding flexibility daily. Your entire body exists because carbon builds stable yet adaptable molecular frameworks continuously. Those stellar atoms eventually assembled into living organisms capable of questioning their origins. Carbon becomes soft, hard, black, clear, or alive through structural arrangement alone entirely. Identity depends less upon ingredients than extraordinary architecture connecting identical atoms together perfectly.